The story of the ozone hole starts with an interesting story about refrigerators and trying to solve some of the problems with refrigerants. I don't know how much you know about how a refrigerator works, so I'm going to pop up a picture right here. A refrigerator works through some of the same concept that we've already talked about. So remember, when we talked about energy, we talked about converting a liquid into a gas, and how in order to convert the liquid into a gas, we have to put energy in. So in other words, if we want to convert liquid into a gas, then this is going to absorb energy. And if we want to go the other way around, gas going into a liquid, condensing, in other words, then this is going to send energy out. It's going to release energy. And this is the way that a refrigerator works. So a refrigerator is designed to pull heat energy from the inside of the refrigerator and pump it out to the outside of the refrigerator. And it does this by, well, at least it used to do this, and in some cases it still does. It does this by cooling and heating a liquid or a gas, sometimes also condensing a liquid in a gas and evaporating a liquid in a gas. So we'll go ahead with the evaporation and the condensation. So if we are going to evaporate the liquid, that's happening inside the coils inside the refrigerator, because then it can absorb the energy from inside the refrigerator, and then as the as the gas flows out of the refrigerator, then it can be condensed into a liquid, right here, into a high pressure gas, and we're going to allow it to release its energy out into the environment and then transition back to a liquid. So this is the cycle that happens to cool refrigerators. And so you'll hear words like compressor, evaporator, condenser. These all have to do with phases of matter and what we're doing with them. And we can understand them really well based on the chemistry that we've already studied. So this is how refrigerators work. And I don't know about you, but I pretty much rely on my refrigerators. And interestingly enough, they really were not in home use until about 100 years ago. So the first refrigerators that were available for home use were about 1915. And these refrigerators used ammonia or sulfur dioxide or methylformate or a variety of other kinds of gases. And the problem with these gases, they work perfectly well. The problem is if you had a leak, then you either had a toxic gas or you had a flammable gas. And so, unfortunately, some people died because of the toxic gas or because of explosions. And leaks were not super uncommon. And so the refrigerator companies were really trying to find a good solution to what to use for a gas. I mean, what you want, right? You want something that is inert, it's not reactive, at least not toxic, right? Not reactive. Non-toxic, not flammable, but you also need it to be able to go between the liquid and the gas phase at reasonable temperatures, right? You want to go from, you want it to be refrigerator to room temperatures. Our refrigerator is about 40 degrees Fahrenheit on the inside, and on the outside we have our house at about 70 degrees, but it might go higher than that, right? They didn't have air conditioning, so it might be as hot as 100 degrees inside your house. Ugh. So you have to be able to deal with the gas being able to condense into a liquid at temperatures that are going to be just room temperatures. So it needs to be volatile in that it needs to evaporate easily. So it needs to easily go between this liquid and gas phase, but not so volatile, not like explosive volatile, just able to evaporate. So a team of researchers at the Frigidaire company, led by Dr. Thomas Midgley Jr., investigated some compounds that were based around methane but involved fluorine because they already were known to be volatile. I mean, most hydrocarbons that are pretty short are volatile, right? Methane, propane, butane, those kind of things. Most of them you can use in the gas phase at room temperature, but the fluorine-containing compounds were chemically inert. So the first gas that they investigated and decided that it was going to work, they called Freon. And it has the chemical formula CCl2F2. So it's based on the structure of methane, but instead of the hydrogens, it has fluorines in all of its spots. And this was an incredible compound. It was totally unreactive. It was gas at appropriate temperatures and liquid at appropriate temperatures. It didn't even dissolve in water. So, it didn't want to do anything. It didn't want to react with anything. It was perfect. It was non-toxic. I think there was a demo where they, inhaled it or something and showed that there were no ill effects. So these were so incredible that they came up with some additional compounds too. So this one later got named Freon 12. And then there was Freon 11, which was the same but had 3 chlorines and 1 fluorine. And then they had some hydrofluorocarbons, right? So these ones are known as CFCs, chlorofluorocarbons. And when you make these a little bit longer, you can make these hydrochlorofluorocarbons. And these are things like CHClF2 as the most basic one, CF3CH2F. So this would be based on ethene, right? Or ethane, excuse me. So there were several compounds that were based on ethane and on propane. And the amazing thing about these molecules is that they were all really effective at doing what they needed to do in terms of being condensed gases that worked for refrigeration. And they were also used as propellants. So these were in spray cans like spray paint. So spray paint or hairspray. So they were used as refrigerants and as propellants. And because they were non-toxic, they were not volatile, there were no health hazards anybody was concerned about, that nobody in the public sphere really worried about what the CFCs were doing. I mean, they're not toxic, right? The answer was that they don't do anything. They don't burn. They don't do anything. But of course, a few people did worry about it. And we have a couple of scientists who became Nobel laureates. Mario Molina, Dr. Mario Molina, in that they both have PhDs, and doctors. F. Rowland were both professors at UC Irvine. And they did some calculations and they noted that the bond energies of carbon-chlorine bonds and carbon-fluorine bonds were 327 kilojoules per mole and 485 kilojoules per mole. And so they did some calculations. So why don't you pause the video for a minute and calculate the wavelengths needed to break the carbon-chlorine bond and the carbon-fluorine bond, and then tell me what part of the atmosphere these were in. All right, so coming back together, I hope that you had a chance to go ahead and do that calculation. And if you did, you probably found that the wavelength to break a carbon-chlorine bond is 366 nanometers or less. And the wavelength to break a carbon-fluorine bond would be 247 nanometers or less. And both of these wavelengths are going to be present in the stratosphere. Remember that little image of which wavelengths are available from our stratosphere, or excuse me, at different points of the atmosphere? I'm going to bring it up here just now. So let's double check on those wavelengths. 247 nanometers is right around here. And as you can see, this is above the 300 kilometer and, or excuse me, the 30 kilometer and below the 40 kilometer. So at 30 and 40 kilometers up in the upper and middle section of the stratosphere, we certainly have the wavelengths necessary to break the carbon-fluorine bonds. And then down here at 366, well, 366 is around over here, and you can see that we have lots of 366 nanometer light pretty much everywhere at all elevations, from up high all the way down to ground level. We have some. And so there's plenty present and in the stratosphere. And this, in fact, is the one that we have a lot more of. That this is going to be the one that we are the most concerned about in terms of breaking off the carbon-chlorine bond. And this is exactly what Dr. Molina and Dr. Rowland predicted. So I'm going to show you that journal article here really quick, just briefly. It's going to be on the Moodle in case you would like to read it a little bit later. So the Molina and Rowland paper was published in Nature and in 1974, and they talked about exactly this. They talked about the photolytic dissociation of CFCl2 into, or excuse me, CFCl3 into CFCl2 and Cl, and this, so this is Freon 11 and Freon 12 into the same, releasing a chlorine radical in the 20 to 40 kilometer range. And the reason that they were interested in this range is because this is where we get the majority of our ozone. And so they talk about this process here, and they go on to warn against the dangers of CFCs at ozone depletion. So relatively quickly thereafter, there did start to be some limitations on what people could use CFCs for, but it wasn't until 1985 when the British Antarctic Survey reported that the ozone levels over the Antarctic had decreased by 50% in early spring relative to average readings over the previous 20 years, and that was when people started to really take notice. So in 1985, this was the first year that the ozone hole was really noticed. In a big way. And although they had a lot of pushback right away, Molina and Rowland eventually did prevail and convince people that it was the CFCs causing the ozone depletion, and they ultimately received the Nobel Prize for their discovery. So let's take a little closer look at what's happening with the CFCs, and we'll look at this destructive cycle from the standpoint of initiation, propagation, and termination. So, initiation, we said, was when our freon would absorb some light and break off a radical. And it's worth noting that actually both of these species are radicals. If we think about that structure, from the Lewis dot structure standpoint, we know chlorine has 7 valence electrons, and so it would have formed a bond here with this carbon, and when we break that bond, both this carbon and this chlorine are radicalized. But this one does not present the kind of catalytic destructive power that the other one does for whatever reason. So we could also have the same thing, of course, happen with our Freon 11, because the important part is that carbon-chlorine bond. Oh, I missed a... That's where the 2 belongs. All right, so one of these is going to be our initiation cycle. And the same thing happens with the HCFCs as well, but we're not going to write them all out here. So the propagation step looks just like that generic catalytic destruction pathway that we talked about in the previous ozone kinetics video, where the radical reacts with the ozone, picks up an oxygen atom, and makes some oxygen gas. And this happens quite quickly because it's reacting with a radical there. That CLO is still a radical, and so it reacts with ozone atoms in the environment to regenerate that chlorine radical and produce another oxygen. And this happens even faster because it involves 2 radicals. And so our net reaction is just what we have seen so far, that it's the ozone reacting with an oxygen to make 2 oxygen molecules. And this continues. This chlorine radical can destroy many, 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 many ozone before termination under the right circumstances, which we'll talk about in a moment. So the termination, we can have this middle step, the CLO, interact with a nitrogen dioxide to make ClONO2, or we can have the chlorine radical directly interact with some water molecules to make hydrochloric acid and hydroxyl radical. But the only thing about these is that both the ClONO2 and the HCl, these are called chlorine reservoirs or chlorine radical reservoirs, because the chlorine radical can come back out of both of these under the right circumstances. And so unless you can do something like precipitate it out as part of rain, dissolve it and get it out of the atmosphere that way, then those chlorine aren't really out of the, out of service for very long. So this cycle, even though, it doesn't look great, there's not so many CFCs in the atmosphere, and this wouldn't be a problem if there weren't some other situations as well. So let's actually go ahead and take a look at the ozone hole. There's a website that tracks these, actually more than one. The one that we're going to look at is Ozone Watch, which is run by NASA. This is really a pretty cool website, and I hope that you come and take a look at it. It tracks the ozone, and the information is published here. So we're actually going to do some stuff with this website in our lab activity, or one of our lab activities this week. And so let's take a look. This is the ozone today, or maybe it was yesterday. Let's check. Okay, so we have it through the 13th. This is our average ozone for July. This is real-time data. So it takes them a couple of days to get the information posted, but that's understandable, right? So today's the 15th. So we just have 2 days of lag here, but those 2 data points will get filled in. So we actually need a little bit more information before we can understand what we're looking at. We've got a pretty swirly pattern here. Let's take a look at this graph. So this graph has the ozone represented in total ozone in terms of this unit called Dobson units. And we have a relative picture here where we go up to 700, which is bright pink, and then between around 500 it's red, and then 400 is yellow, and then we go into green around 300, and then blue is around 200, and 100 would be purple. So we've got this nice rainbow scale that we can take a look at. But let's go back to our notes and talk a little bit about what Dobson units are, because this is a new piece of information. Okay, so if you look at the Dobson unit, we have the definition of a Dobson unit in our book. I think it's in one of the problems. You can also find it on the NASA website as well. And the Dobson unit is equivalent to 0.01 millimeter of ozone at 0 degrees Celsius and 1 atmosphere. And when I read that definition for the first time, I think, how can I have 0.01 millimeters of ozone? This would be equal to 1 Dobson unit. What does this even mean? So if we look at the NASA website, they do a little bit of a better job of expanding what we're talking about. They say, all right, imagine that we take a column of air. So this is a volume, right? Okay, I'm trying to draw a column of air. So imagine that it's like a little, I don't know, skinny Lego block. And here's the surface of the Earth, and then up here is the ozone layer in the stratosphere. And we go all the way up to include all of the ozone that's present in the stratosphere. And what they're seeing is that if we have this column of air and we took all of the ozone and we stacked it down at the bottom of that column at 1 atmosphere, which is atmospheric pressure for us, and 0 degrees Celsius, which would be kind of chilly, then this 1 Dobson unit above us would stack up to 0.01 millimeters of ozone. 1 Dobson unit is pretty small, so 300 Dobson units of ozone is average. So if we take 300 times 0.01 millimeters, then we would find that would stack up to be 3 millimeters of ozone thick. If we took all of the ozone in our column from the very top of the ozone layer and just squished it flat down to Earth, it would only make a little stack 3 millimeters thick. So hopefully that makes a little bit more sense. If we were to put it in a 1 centimeter by 1 centimeter by however much is appropriate, I think 300, so 3 millimeters high, then the number of ozone molecules in here would be about 2.69 times 10 to the 16 ozone molecules, and they would be stacked at 1 atmosphere and 0 degrees C and a volume that would be 1 centimeter by 1 centimeter by 3 millimeters thick. And so now you would be able to use PV equals nRT to figure out the number of moles and prove that this is the number that are present. Okay, so hopefully Dobson units makes a little bit more sense. And if we go back to the Ozone Watch website now, and we say, okay, if 300 is kind of our average value, we've made that a nice green, we can see we're pretty close to that average value right now. And this is true, this is the southern hemisphere, we're looking at Antarctica here. So this is pretty true for the horizon that we can see, for as much as we can see. That everything is all pretty okay in terms of our Dobson units. But as we go toward the blue, and you can see we're sort of edging there around here, this is where our ozone is getting a little bit thinner. So we're going to look at some videos of how the ozone changes during our activity tomorrow. But the short version is that we will get I don't know, what the heck. Let's do it now too. All right, we find the videos over here under multimedia. And you can see that we have ozone movies for both the southern hemisphere and the northern hemisphere at various different sizes. So let's just go ahead and pick a year. Let's look at 2010. So this starts in July, and we can see some swirls of higher Dobson units where those red areas are. But you can see that blue, that nice cobalt blue forming by September. And we have this nice sort of wobbly circle, which is the ozone hole, which is happening in September and October and November. And now at the end of November and into December, we're starting to swirl it away, and then it's gone. So we have a seasonal effect because it's not constantly there. By the end of December, that ozone hole is gone. And when we started in July, that ozone hole wasn't there either. So let's talk about those seasonal effects. So what do you know about Antarctica in August, September, October, November? What season is it? I have to think about this too initially because I am only, immersed in my own season. But you have to remember that the seasons in the southern hemisphere are opposite of the seasons in the northern hemisphere. So for us, July is midsummer. So in Antarctica, July is going to be midwinter and heading towards spring. And even though there's not a, super spring-like spring, they still do have some variations in the seasons. So what you get in Antarctica in the very beginning of winter you get this formation of polar stratospheric clouds. These are very thin, very high, obviously they're in the stratosphere, very cold stratospheric clouds. And what happens in the stratospheric clouds is that you get a set of collection of these chlorine radicals, of nitric oxide, of dust. You get ice crystals that form. And all of this catalyzes the formation of these chlorine radicals. And then you also get the formation of a polar vortex. Do you remember how you saw those swirling clouds, like pretty much just making that little oval right over the pole? That's the polar vortex. And when you get the polar vortex happening there, then you don't get a lot of mixing. So this is little mixing with outside warmer air, or, with other air that's outside of the polar vortex. Just kind of has a little swirl pattern that sets up. So it's very cold. It's very dark. And so you have this buildup over time of these of a high concentration of chlorine radicals, nitric oxide, ice crystals, and stuff. And so when we start to get to the end of winter, which is the beginning of our fall, right? Yeah, because we're going to transition. They're going to transition into spring when we transition into fall. So we transition into fall in September, and they transition into spring in September. And so at the very end of winter, then the light starts to return. And because we now have some sunlight, we have some ultraviolet wavelengths ready that are going to cleave that chlorine bond, produce chlorine radicals, and start destroying ozone. And they do it. And because there's not a lot of light and it's still very, very cold, it's difficult for the process of the Chapman cycle to regenerate ozone in this process. So it takes a while for the ozone to recover. It does recover, and seasonally and in other parts of the world where we have, where we don't have absence of sunlight or super cold temperatures, then our ozone stays pretty constant. Now, it doesn't stay constant because it would definitely stay constant if we had kept using CFCs. But after Mario Molina and F. Rowland brought the world's attention to the CFC ozone problem, there started to be restrictions on use of CFCs. And after the 1985 Antarctic discovery of the ozone hole, people kind of freaked out, and they actually took it seriously. And the Montreal Protocol came about really quite quickly afterwards. 1987 is when it was signed, and the restrictions started going into effect soon thereafter. So the Montreal Protocol limits and phases out the use of CFCs and compounds in the same family with the CFCs. And we are seeing recovery of ozone. So this is a success story, and we need some success stories, right? We need to feel like, hey, we did something. We noticed that there was a problem, we acted, and things are happening. Now, it's still going to take a while. Don't let people tell you the ozone hole is not there. It is still there, but it's recovering. And the last estimates I heard was that the Arctic hole should recover by the 2030s, and the Antarctic hole by the 2050s. So we should still be alive when our ozone holes are just a thing of history. And this is cool, right? This makes me feel really optimistic that we can make positive change. So on that positive note, we're going to finish this particular lecture, and I'll develop our lab activity and get you some more problems to look at.